Welcome back. Now we're going to look at energy conservation. Remember, this entire class is centered around one question. Where's the energy go? So first, what is energy? What you need to know, it's a scalar quantity. What's this mean? No direction. Which means normally when you talk about physics, you worry about vectors and start there. We're going to start with energy. You don't have to worry about directions. Two types, kinetic with motion, and then potential, which will be associated with position. Let's define some types. First, we're going to look at translational kinetic energy. This is just the ball is spinning in circles. It's moving around. It is independent of direction. It doesn't matter if it's going to the right or to the left. Since it's squared here, it's always going to be the same. And it is possessed by a single object, where m is the mass of the object, v is the speed. Second is gravitational position, or potential energy. This arises from the difference in potential energy due to gravity. So when you let two things go with mass, they will come towards each other. This is how much energy you can hold. Again, both objects, so m1, m2 are the masses of your two objects, distance between your objects, and then this gravitational constant, which in August 29th, 2018, they measured again to more decimal places, so we don't know everything yet. If you use a Taylor series expansion, remember Calc 2, remember Taylor series? You can find that your first two terms give you this potential energy due to gravity at the surface, and mgy, where y is just the height above the surface of an object, and you get to pick where your surface is. This only works if y is a lot smaller than the radius of the Earth. And again, g, the value mg, this little g, comes from values at Earth. This is just what we talked about, potential energy, and your gravitational acceleration. Final type that we're going to talk about is a spring. So with a spring, you squish the spring or you compress the spring, it tries to pull you back, right? So what we'll find, we take the spring, we squish it, that gives you your delta L. This is the change in length of the spring, where L is how long it is now, and L0 is where your spring would be. It's your equilibrium position, just where it would be if you let it go. So the main idea is energy conservation. Energy can't be created or destroyed. It's got to go somewhere, all right? And we're going to figure out where. So let's talk about isolated systems. All this means is that delta E is equal to 0. So energy is not going to leave. It will later, but right now we're going to look at isolated systems. First example, we have a rock. This rock is going to fall, as rocks are known to do. We want to figure out how fast it's going when it hits the ground. So when we're looking at this, we know it's going to be a conservation of energy problem. We know the total change in energy is going to be 0, which means that the total change in potential and kinetic energy is also 0. So let's look at the potential energy due to gravity first. We've got our base value at the surface of the Earth, and we can see that those are going to cancel. That's why a lot of the times those are neglected, and you just see it as this portion right over here. They cancel out, giving you your change in potential gravitational potential energy, which hopefully we've seen before. If not, here it is. It's pretty neat. Moving forward, let's look at this kinetic energy part now. mvi minus mgy. Well, do we know any zeros? Well, yeah, it's not going anywhere at the beginning, so that goes away. And it lands at the ground, which we'll conveniently call 0, so that goes away. And we are left with an expression, which, again, solving with variables first, as we should always do. We're trying to get VF by itself. Oh, look, we've got an expression. Now let's plug in some numbers. So when we're plugging in the numbers, we're going to find out that we get this squared term here. And this square is going to give us this plus or minus. So how do we know? You always have to check with reality. It's falling down, so the velocity is going to be negative. But just always know, whenever you take the square root, you get this plus or minus, and then you have to compare with what's actually happening in the world. Now let's do an example with the spring. So we've got this block, it's going to squish the spring. So the spring is actually going to get shorter. Again, we start with conservation of energy, except now we have this new fun spring term. So let's look. Delta E is 0. Again, isolated system. And gravitational potential is 0. Why is it 0? Well, it's not moving up or down. That's the only direction that matters with gravitational potential energy. It's not getting any farther away from the Earth's surface. So that way, that is 0. And we plug in our formulas for kinetic energy and potential energy. Is it going to be stopped anywhere? Well, yeah, it's going to stop at the end. And the spring's not squished at the beginning, so those go away. And we are left with this formula, mv squared k delta L. We're going to find this delta L, so let's keep on going. Isolate it in our equation, plug in our numbers now that we've got this, and I know delta L is now 0.16 or plus or minus 0.4. How do we know if it's plus or minus? Well, the block's going to hit it, the spring is going to squish, checking with reality. We know that delta L is going to be equal to minus 0.04 meters. Since the spring will be compressed during the collision, the final length of the spring will be less than the unstretched spring, which makes sense. It gets shorter because you squished it. Hopefully that helps. Again, isolated systems, change in energy is 0. I will see you in class.